Hello, class. Welcome to this lecture, which deals with the topic of forecasting. Uh, really, on this lecture, what we're going to be focusing on is time series forecasting. And bullet number one for your learning objectives lists some of those methods that we'll be looking at. We'll look at ways that we measure error in forecasts and how we can come up with statistics that will help us to use that understanding of likely error in order to better make decisions that incorporate that information. It's very unlikely you'd ever get a forecast to be exactly spot on, so it's worth knowing plus or minus how much you need to plan for. Along the way, we'll distinguish between various elements of demand and talk about how to compute those things and put them together to make the forecast. We'll talk about seasonality and how to deal with that. And at the end, we'll briefly mention a newer technique called CPFR, Collaborative Planning and Forecast Replenishment, which helps us to get better information and do a better job with our forecast. So I hope you enjoy it. So when we talk about a time series, your book says it's the repeated observations of demand for a service or product in their order of occurrence. Well, that would be a demand time series. We could have any number of different time series. So basically, it's just the values of a variable over time. So if you put the variable time on the x-axis and the whatever it is you're measuring on the vertical axis, you've got a time series. When we think about forecasting a time series, mathematically what we try to do is we try to decompose it so that we can measure the parts of the time series and put them back together. So the things that we might see in a time series, we're always going to see random variation. So, there's virtually no demand pattern or time series pattern where the next period's value is 100% predictable 100% of the time. Otherwise, there wouldn't be much reason to think about forecasting. It'd be a trivial exercise. So other things we might see are an upward or downward sloping trend or no trend, which would be a horizontal pattern. We might see seasonality, and seasonality could be the annual seasons like winter, spring, summer, fall, based on weather cycles, but they don't need to be annual. All they need to be is predictable cycles. So many cycles are predictable on the basis of day of the week. Take, for example, demand in the cafeteria on campus during a regular semester. And no doubt the demand on Saturday is very different from the demand on Monday or maybe even Tuesday because of Tuesday, Thursday versus Monday, Wednesday classes, and so on. So there's probably a weekly cycle. If you think about this pandemic we've just been through, you've probably seen a number of times and maybe you watched with great interest the number of infections that were being experienced in your county. I'll bet you if you looked closely at the charts that you were being shown, there was some sort of a smooth line that cut across and sort of said this is what we averaged for the week. But if you looked at day by day by day by day, I think most of us saw much higher reported cases like on Monday than on the weekend. And well, that's just because the reporting was seasonal. It's probably wasn't the case that you were more likely to catch COVID on Saturday than on Friday, but it probably was the case that you were more likely to get help and have a reported positive test on Monday than, say, Saturday, or even Friday than, say, Saturday. So the demand was seasonal, and the day of the week was a season. Cyclical patterns are unlike seasonal patterns in that their duration is not so predictable. So The most common example we could talk about here is the economic cycle, where we have periods of growth and we have periods of recession. We don't know when the next recession will occur. We don't know how long that recession will be. Certainly, most people were surprised by the COVID pandemic and the recession that occurred right at the beginning of it, and then were surprised that it was such a short recession and the recovery was so rapid. I think government stimulus activities and activities of the Federal Reserve had a lot to do with that. But of course, nobody could predict how long that cycle of growth and recession might go. So those are things that we'll look for, and as we estimate the individual components of demand, then we'll build potentially a forecast that assembles our prediction on the basis of our estimates of the underlying components. Next few slides just show you what we mean by those components. Here we have a horizontal pattern with just random variation, obviously no positive or negative trend. Here we have positive trend. We could have shown some negative trend, but in this case they're just showing positive. And so that's what we mean by a pattern with trend and some random variability. This pattern shows seasonality. You'll notice that September and October were high demand periods in year one, and then lo and behold, same thing happened in year two. And then November and December were lower in year one, and again somewhat lower in year two. So there's variation from one year to the next in terms of how strong that seasonality is, but we see a pattern more or less repeating itself from one year to the next. So this is a case where we have seasonality and it's on sort of an annual basis. It looks like they're treating particular months as seasons the way this is drawn. Of course, here's a cycle. We don't know how long the cycle is going to be, but we just have a demand pattern where there are both periods of negative trend and periods of positive trend, and perhaps in between them troughs and peaks, and so it's a cyclical pattern, but we don't know how long the cycle might last in any given instance. So when we're thinking about putting together a forecast, one of the things we've got to think about is what are we going to forecast? So one thing that we'll think about is the level of aggregation. Are we going to forecast demand for individual items? Are we going to forecast demand for product lines? Are we going to forecast demand for all of what happens in a given production area? Product segments, so the level of aggregation has to do with how much we're putting together into our forecast, and sometimes we might even think about the length of time that we're dropping into the forecast. So is it going to be based on hourly demand, daily, weekly, monthly, or some other level of time aggregation? And then we might think about units of measurement. Again, this might be individual items that we're measuring the demand for. Maybe product families, could be thinking about things a variety of ways. And so the first thing we've got to do is decide exactly how we're going to measure what we're going to measure and what the level of aggregation is going to be. You kind of get the picture there. So the second thing we're going to think about is, okay, how are we going to forecast demand? So in this chapter we're focusing mostly on time series forecasts, and those are really good for short-term forecasts because what happened yesterday is a pretty good indicator of what might happen today, or what happened today, pretty good indicator of what might happen tomorrow. What happened last week, not such a bad indicator of what's going to happen this week. If we think about last week, it's not as good of an indicator for, last month, maybe not as good of an indicator for what's going to happen 2 months from now. Or let's say what happened last year might not be a great indicator for what's going to happen a year from now. So time series are particularly good for short-term forecasts, and they're different from these from causal methods in the sense that time series looks only at the patterns in the variable of interest, whereas with causal methods, what we try to do is we try to find something we can measure today that's related to a variable that we're trying to forecast. So for example, the number of, let's say, housing starts in a small town might be related to the demand for, let's say, carpet some months later. Or perhaps you might say in Statesboro, we can measure the number of students who signed housing leases and for the coming school year, and that could be related to the demand. Let's say even though the leases were signed maybe in the spring or summer, that may be very much related to demand for, let's say, pizza or tables at a restaurant or things like that, where you would see students, even groceries of various types. That's the idea in a causal method. It's not that students signing apartment leases causes there to be demand for pizza, but there's this relationship. If we know how many students signed leases, we're going to have an idea about how much of the product we're selling that students consume might be needed in months to come. That's sort of the idea and difference between causal methods and time series analysis. So your book talks about trend projection using regression. So that's using regression as a time series method. We could use multiple regression, which treats it more as a causal method. So you probably saw this in your stat class, and certainly would see it in your BUSA 3132 applied regression and optimization course. So trend projection using regression is a time series approach to using the regression tool. We'll look at that. Finally, there are judgment methods of forecasting. So if we're really thinking about long-term forecasts, I might ask you, do you think that there's going to be a need for more classrooms in Statesboro as we look toward 2040 and 2050? Well, that's interesting. Yeah, we're probably not going to try and come up with a specific number, but we're probably going to try and understand what higher education might look like in 2040 or 2050, something like that. Really interesting. So, for example, what might be the demand for paper in 2050? Is everything going to be online? Are we going to print anything out, really? Okay, so then what's going to be the demand for cloud storage? So these are things that generally we're going to rely on, let's just say, the expertise of people that in their business have to think about these long-term decisions. So judgment methods tend to be long-term. They tend to be more qualitative and less quantitative. The causal methods we're talking about tend to be more intermediate term, and they tend to use econometric models, one of which would be multiple regression. And then time series analysis is a short-term approach to forecasting, using just the variable of interest and deciphering the patterns in that variable in order to make our forecast. So one thing you know about forecasts is they're going to be wrong. And it doesn't matter what method you're thinking about, there's going to be error in the forecast. It's important to measure that so that you can plan for the range of possibilities. It's important to have a forecast that gives you a number, but it's more important to understand how far off, over, or under that error could be. So when we think about forecast error mathematically, it's simply the difference between what happened and what we forecast. So we would say that's D sub t, which is what happened, actual demand in a given period, minus F sub t, which is the forecast for that period. So we use that measure in order to sort of understand where our forecast could be wrong and by how much. So one thing that we could measure is, it's called CFE, the cumulative sum of forecast errors. It's just the sum of the error terms that you've gotten over time. We call it bias because what we would like is a technique where sometimes we overestimate, sometimes we underestimate. So when we add up what's happening over time, we end up with a value of 0. The positives and the negatives cancel each other out. So if we end up with a CFE of 0 or very close to it, we'd say our forecasting technique is not biased. We know that linear regression gives us an unbiased value for forecasting error. Just it's something we know about the technique. But if we find over time that the CFE is large or getting larger, then if it's large in a positive way, we know that typically F sub t is less than D sub t. So we're consistently underestimating demand. And if we see that, we know we're doing something all the time, then we can correct for it because we've been doing it all the time. So there's also something that we could use that gives us the same kind of information that we would call mean forecast error. Your book here calls it E bar. I might just call it MFE for mean or average forecast error. So if you know the number of error terms you're using, you can calculate the average of the error terms. If you square the error terms and divide by the number of error terms, you'd get the mean squared error. And this is a lot of times, because it's related to the standard deviation, it's something that's of interest to us. It's something that's just calculated in the process of coming up with a forecast when you're using regression. So it's something of interest to us in that sense. Obviously, a squared error term is always going to be positive. So when we calculate the mean squared error, we lose some information about the sign of the error. But when we take the square root of it, it's what we call, you would know, it looks very much like a standard deviation. So a lot of times we call it the standard error term. Instead of taking squared error terms, if we take the absolute value and calculate the mean, then we get the mean absolute deviation, or the MAD. And we can also calculate on a percentage basis how big the MAD is, and so that would be the mean absolute percentage error. These will help us to think about planning if we create a forecast, and so we know it's not biased, and we know on average how much it's off by, that's the MAD, or if we know the standard error or the percent error, then that enables us to make our contingency plans and be ready for whatever might happen, whether the forecast is over or under by a large amount or a small amount. So let's walk through an example that shows us how to calculate these error terms. You'll notice that we have 8 months worth of demand information, the information about demand in the column labeled demand, obviously. So there's an 8-month time series. We have forecasts. We don't know exactly how those were prepared, but we don't need it for this purpose. So the difference between demand and forecast gives us the error for any of those 8 months. The cumulative forecast error, the sum of those numbers, is negative 15. So they're positive and negative terms, but the cumulative sum of all of those, negative 15. If we square the error terms and add those up, we get the sum of the squared error terms. And similarly, if we take the absolute values, we can get the sum of those, or if we convert those absolute values to percentages, we can get the sum of those. Dividing those totals by 8, would give us E bar, or the mean forecast error, mean squared error, mean absolute deviation, and mean absolute percentage error. So we'll see that on the next couple of slides. Here we are. The CFE is negative 15, and so the MFE, or E bar, is 15 over 8. The mean squared error is the sum of the squared error terms divided by 8. And continuing on, the cumulative, oh, I'm sorry, we already have this one. So the MAD, or mean absolute deviation, is the sum of the absolute values of the error terms divided by 8, and the mean absolute percentage error is the sum of the percentages of the absolute error terms divided by 8. So typically we're away from demand by 10.2% of what the demand value is. That is on average, and typically the absolute value of our error term is 24.4. So if we had a forecast for, let's say, 300, well, we would have an idea about how close to that we need to be ready to plan for. So to be more specific, our cumulative forecast error shows us that there's a slight bias over this 8 period forecast. So because the value is negative and the error term is demand minus the forecast, we know that the forecasts on average are smaller than the demand. So planners might start fudging a little bit if this was really a persistent thing. And they might say, okay, the forecast was 300, but it's always a little bit, forecast is always a little bit low, so we're going to plan for 315 or something like that. The MSE, the square root of the MSE, sigma, and MAD, they provide measures of the extent on average of the magnitude of demand. So MAD of 24.4 means on average we were off by 24.4. The value of sigma, which is the square root of the MSE, tells us that the distribution of forecast errors has a standard deviation of 27.4. So you'll see that sigma is a little bit bigger than the MAD, and it's common maybe to find that a value for MAD might be something like 3/4 of what sigma is. So in this case it doesn't come out quite that way, but generally a MAD will be smaller than sigma. And the mean absolute percentage error of 10.2 tells us that on average the forecast error was about 10% of what the demand value was. And so we may be able to see this get better as we move through time and maybe adjust forecasts. If there's one really big error term and we only have 8 periods, then it's having an outsized impact on these error terms. All right, let's talk about methods for forecasting now. We'll start with linear regression. As it's applied to time series, we would have our horizontal axis, or independent variable, would be time. So if you've got y equals a plus bx, or if you like mx plus b, you've got the slope-intercept form of a line. So we're not saying that time is causing the variation, but we're saying that we can use a straight line to estimate the variation. One of the things we get out of linear regression, and one of the times when it's really useful for us, is when there is trend. So the slope in the function for a line obviously is our indicator of trend in our demand pattern. So hopefully this terminology y equals a plus bx instead of mx plus b. That shouldn't trip you up here. It's just the equation for a line where the slope is whatever the coefficient is that's applied to x, and the intercept is the value of the term that doesn't have a variable attached to it. So essentially what we're doing with linear regression is we're trying to fit a line the very best that we can to the values that we see over time. And actually the linear regression approach, minimizes the sum of the squared errors between the individual observed values and the estimated line of regression. So let's talk about how we might use regression in forecasting. So the example here is just that a supply chain manager thinks that a better way to forecast demand is to understand how it relates to advertising. That would be a causal approach, by the way. We're going to look at advertising and think about how sales relates to that. So the company will spend a certain amount on advertising for the product, and we want to determine what the impact of that might be. So what we'll do is we'll use regression to evaluate that. The problems from the book tell us to use POM for Windows or to use OM Explorer out of my OM lab, but I think that's probably not a good way to go about doing this. Number one, you're not going to have those after you're done with this class, but then number two, it's not hard to do in Excel, and you will have that later. So what we want to do is use the data analysis add-in for Excel. So when you select the data menu from the top Excel menu, you should see on the far right an option that's data analysis, and it's in the analysis box. If you don't have it, then you need to go back and click File and Options and Add-ins and get that analysis tool pack. If you are unaware of how to do that or having difficulty doing that, I can probably help you with that. So once you've got the data analysis add-in, what you're going to do is you're going to go there and you're going to select regression, and what's going to happen is a wizard will pop up, and you'll just select the appropriate data cells for that wizard, and the regression output will be given to you. Let's take a look at how that works. So what you see here is that I've entered the sales and advertising data that was given a couple of slides back, and I've brought up the regression wizard. So the input Y range is the information that we have about demand. It's the variable of interest. We would call that the dependent variable. And the input X range that we would enter is the information we have about the independent variable. That's what we would call advertising in this particular example. So in our case, we do have data labels. So we've got month by month by month, and the first row, of course, is the label for the variable. So we click that box that says labels, and then we enter a cell where it can put the output that we're interested in, and I just put A10 there, something down below the data out of the way. And when I click OK, if I've got these values in these cells, then it's going to give me the output that you see actually that you see here, but let's go to the next slide. So here's the output that we get when we do what I just showed you with the Excel solver, the data analysis tool for regression. So it tells us there's an intercept of -8 and a slope of 109 in this case. So we get y equals minus 8 plus 109 times x. So basically, if we think about how much sales we get per dollar, it looks like a lot, yeah, per dollar of advertising. So if we wanted to create a forecast using this information, what we could do is we could create another column here. We'll call it forecast. And just for period 1, it would be minus 8.135 plus 109.229. Period 2, it would be minus 8.135 plus 109.229 times 2, and so forth. So that's essentially what you see happening here. If advertising is 2.5, then using this forecasting technique, minus 8.135 plus 109.229 times 2.5 gives you 264.9375. So in the problem, the example, it said we're thinking about spending $1,750, 1.75 thousand, the way the data's been entered here. So what would be the forecast in terms of sales? Well, in that scenario, the forecast is 183. Now we can look at the error terms as well, and we can see that the MAD is 8. So, if we were off by 3 or 4 MAD, then we might be down around 160 or up around 200, 200 plus, 210 maybe. So we would want to plan according to that. We notice that the CFE there is 0 essentially. So like we said, regression is an unbiased forecasting technique, and lo and behold, we end up with essentially no bias. Okay, let's keep moving. Okay, so let's start looking at some time series methods. A lot of times, if we want to forecast what's happened tomorrow, we just say, well, what happened today? And that becomes our forecast for what's going to happen tomorrow. How many people are going to show up for my next class? Well, how many showed up the last time that class met? So that approach is what we refer to as the naive forecasting approach. Naive doesn't, it has a negative connotation the way that we apply it to people, but here all it really means is it's a simple approach. Naive is a synonym for simple. And so the simplest thing we could do is just say, okay, what happened last time? That's going to be our forecast for this time. We could say that that's a 1 period moving average, if you like. It's a forecast based on the previous period's demand. So that's pretty good. Generally, we may not like a naive approach, because if one particular day we happen to have, let's say, a tropical storm coming through and barrels of rain, then maybe we have very few students in class, and when we predict using that approach the demand the next day, the number of students that show up the next day, well, we're way off because the situation is quite different. So when there are potentially significant random fluctuations in demand, we might not like the naive approach, and we might like to include several more periods and average across those periods to eliminate the random variation that creeps into our forecast. And then what happens is the random variation ends up accumulating into the error terms, and that's the way we like it. So our forecast doesn't get jerked around by what's random, but we have an idea about what the range is that we need to plan for. So techniques that take advantage of this idea of averaging across several periods would be simple moving averages, weighted moving averages, and exponential smoothing. So simple moving averages, just whether it's 1 period in the naive forecast, or 2 periods, or 10 periods or 52 periods, simply make the forecast for the next period equal to the average of so many previous periods worth of demand. That's a fairly straightforward thing. So we could look at an example like this. Compute a 3-week moving average forecast for the arrival of medical clinical patients in week 4. And so if we know the previous 3 periods, we can average those, and that'll give us our forecast for week 4. That's not too difficult. When we get the information about week 4, we can have a forecast for week 5. So here we go. Averaging the 3 periods worth of demand gives us 397. That would be our forecast. For week 4, we find out that the actual demand was 415. Then we had an error of 18. We overestimated by 18. But now we have a new data point, so we'll drop off week 1 and look at the average of weeks 2, 3, and 4 in order to have our forecast for week 5. And for week 6, it would be the average of weeks 3, 4, and 5, and so on. So that's why we call it a moving average forecast. A weighted moving average is very much like a simple moving average, except that we don't give equal weight to each of the prior periods that are included in the average. For example, in the last example where we computed the moving average, we were dividing by 3, or you could say we were giving a weight of 1/3 to each of the 3 prior periods that were included in the average. Well, we don't actually have to weight those prior periods equally like we did with the simple moving average. In fact, we might think, well, what happened more recently is more important to what our forecast is than 1/3 of the weight, and so we could give that, let's say, 2/3 of the weight and split the weight between the others with I guess 1/6 apiece. So we're weighting differently. So let's see how that works. Here's the example. We're saying that we've seen demand of 790, 810, and 740 on days 4, 3, and 2 respectively. This is customer arrivals. And so we're going to apply a weight of 0.5 to the most recent period, 0.3 to the period 2 days earlier, and 0.2 to the period 3 days earlier. So if we're trying to forecast demand or arrivals in day 5, then we'd take a weight for 1 day back and multiply it by what happened in day 4, a weight for 2 days back, multiply it by what happened in day 3, and a weight for 3 days back, multiply it by what happened in day 2. And so we end up with this expression and a forecast of 786 customer arrivals. So if we had 805 that arrived, we'd end up with an error of something like 19. So if the actual number of arrivals was 805 on that day, now we could get the forecast for period 6 using days 3, 4, and 5, and just the same way that we did before, and we'll end up with a forecast of about 802 customer arrivals. All right, let's talk about exponential smoothing then. This is really a weighted moving average technique. It's called exponential smoothing because the formulas reduce the weight as time moves further and further away from the current period exponentially, and not make a big deal about that, but basically this is actually a very widely used approach because it doesn't require us to keep volumes of past demand data for every item that we're forecasting. Really all we need is 3 pieces of information. What was the last period's forecast? What was the demand for that period? And what's our smoothing parameter? In other words, what percentage of the error do we think is not random, so that we can use that to make adjustments to our previous forecast. So essentially all we do is adjust the previous forecast by a percentage of the error in the previous forecast. Formula in your book says the forecast for the coming period, the next period, f of t plus 1, is alpha times demand for this period plus 1 minus alpha times the times the forecast that we calculated for the last period. And so that formula is essentially alpha times d of t plus 1 minus alpha times f of t. Or you could say it's equal to f of t plus alpha times the error, which is d of t minus f of t. You could rewrite that formula that way. So essentially our forecast for a coming period is just what the forecast was for the prior period, adjusted on the basis of the error that we experienced in the prior period. Let's take a look at how this works. So just some information about exponential smoothing before we look at an example. Essentially what happens is with large values for alpha, we give a lot of emphasis to recent demand, and the emphasis we give to past demand becomes much smaller very quickly. So small values of alpha treat past demand more uniformly and give less of a weight to the more recent periods. Let's look at an example with exponential smoothing. We'll just use the data you see pasted here from example 3, and we're going to say it's the end of week 3. So we had forecast demand for week 3, let's say, to be 390 arrivals, and the actual number was 411. We're going to use alpha of 0.1, which is to say we're not going to be real responsive to error. We're going to consider 10% of the actual error we observe to be meaningful and adjust our forecast in that way. So we'll look for a forecast for week 4, then use that data to find a forecast for week 5. And we're saying demand in week 4 turned out to actually be 415. So the forecast for week 4 using exponential smoothing is going to be 0.1 times the actual demand plus 0.9 times the forecast. So when we just plug those numbers in, we end up with an arrival forecast of 392 patients. We said on the last slide that the actual arrival rate was 415 when we got to it. So if we look at the next period, we'll say that the error is 23, so I guess we would adjust, since alpha is 0.1, we would adjust upward by 10% of 23. And let's see, our forecast was too low, so we'll adjust upward by 2.3, 10% of 23. And we'll end up with a forecast more like 394.3, 394. Let's see if that's what works out. So using the formula, there you are, 394.4. It's essentially 0.1 times 415 plus 0.9 times 392.1. So there we are. Fairly straightforward process of using the most recent demand, the most recent forecast, and the value of alpha to come up with the forecast for the coming period. With any of these exponential smoothing techniques, if we wanted to forecast more than one period out, it would just be the number that we have. That's our forecast of the level of demand. So if we were to say 2 periods out, 3 periods out, 4 periods out, it's just 394. So that's because this exponential smoothing approach and the moving averages don't have a a way to treat for trend the way that we're using them right now. It's not a subject for our course. There is a way to build that in, but we're not going to do that. So what that means is where we have trend, we're probably going to be better off using regression so that we have an estimate of that trend and we're actually building the trend into our forecast. Let's take a look at how that works with regression. So here we're using regression in a time series sense and not in a causal model like we did earlier in the slideshow. Here's an example. You'll notice we're using the same regression wizard from Excel that we used when we were building a causal model. In this case, the input range for the y values, in other words, the dependent variable, is arrivals. That's where we're going to put our demand information. And the independent variable is the cells that reflect the time period that we're talking about. So we've got the labels in the first row. We'll check that, and we'll give the computer a place to put our output somewhere down and out of the way. The result of the regression analysis that Excel does tells us, if you look at the bottom two cells in the second column here, the coefficients for our intercept and our slope. So the intercept is 28.5 and the slope is 2.34 units. So we're growing demand in terms of arrivals by an average of 2.345 arrivals per week. So I went ahead and drew a graph using information that's included in this estimate. So the red line is the regression line and the blue line is the actual demand data that we used for this regression. You'll see the table from which this chart was developed in the next slide. So here it is. Essentially, the arrivals are what we already were given in terms of data. The forecast is that intercept of 28.5 plus the slope, which was about 2.3 times the particular week that we're looking at. You'll notice the CFE, the cumulative forecast error, is essentially 0, and that's what we expect because we know regression to be an unbiased forecasting technique. The average forecast is off by 6.21. That's what the MAD tells us, or it's off by about 0.135%, very small percent error here. So I'm sorry, not 0.135%, but 13.5%. So it's a small error, but not microscopic in this case. So that's using the time series approach, trend projection with regression. So just to summarize, we've looked at causal approach to regression, we've looked at simple moving averages, weighted moving averages, exponential smoothing, and trend projection with regression. The final techniques that we want to talk about help us to deal with seasonality when we see that in our forecasting technique. You're going to get excited because I said final, but there are a few slides left anyway. So when we think about seasonality, we could treat it as a multiplicative seasonal approach or an additive seasonal approach. With multiplicative seasonality, essentially what we're saying is that the seasonal impact is to increase or decrease demand by a consistent ratio over time. And the additive approach says the seasonal impact is going to be essentially the same amount over time instead of the same ratio of demand. So with the multiplicative seasonal method, essentially what we'll do is follow these 4 steps. For each year, we'll find the average demand across all of the seasons, and then we'll divide the actual demand by the average demand to get a seasonal factor. And if we have seasonal factors for several years, then we'll average like seasons in order to get an average seasonal factor, and we'll use that in order to adjust any forecast for the coming year to include seasonality. Let's see how this works. Let's look at an example, and in this case it looks like we have a seasonal business that's a carpet cleaning business, and we have a peak demand in the third quarter, a trough in the first quarter. And so we're going to have in the next couple slides demand figures for the next 4 years, past 4 years. And we want a forecast for the next year based on an annual estimate of 2,600. Let's take a look at it. So for year 1, we have these 4 demand values. It adds up to 1,000 units. And so if you were to average 1,000 across 4 periods, the average periodic demand would be 250. So in quarter 1, we got 45, not 250. So the ratio to the average is 0.18. Similarly, in quarter 2, the ratio to the average is 1.34. It's over 250. Period 3, 2.08. Period 4, 0.4. The next year, year 2, we saw 1,200. So a quarter of 1,200 is 300. That's the average. In period 1, we found 70 units of demand. So 70 over 300 is 0.23. So the seasonal impact was to reduce demand from the average to 0.23, or 23% of the average. Period 2, demand was 1.23 times the average, or 23% above the average, and so forth. So you'll notice that in quarter 1, the seasonal factor in the first year was 0.18, seasonal factor in the second year was 0.23. We're going to have 2 more years worth of data. I'll jump to the next slide. And you'll notice that in period 1, the seasonal factor was 0.22 in year 3, and then in year 4 it was 0.18. So, some winters are harder, some winters are warmer, So the seasonal variation, the seasonal impact varies in some random way. To get an average seasonal factor, we would average the 4 seasonal factors that we computed across the 4 years. And so the average for quarter 1 would be the average that we found on the last slide of 0.18 for year 1, 0.23 for year 2, 0.22 for year 3, and 0.18 for year 4. We average those 4 things, we'd have a average seasonal factor for quarter 1. And we'd do the same thing for quarters 2, 3, and 4. So there are the averages. In this case, you'll notice that the average seasonal factor for quarter 1 was 0.2043. And we've sort of averaged across the random fluctuations. Now, we were told a few slides back when this example was presented that there's a forecast for next year of 2,600 customers. So the average per quarter, if we do 2,600 in a year, would be 2,600 divided by 4, which is 650. But we found historically that the seasonal effect of quarter 1 is to reduce demand so that it's only 20% of the average, or 0.2043. So multiplying the 650 by 0.2043 would give us a forecast of 133 essentially units of demand in period 1. Do the same thing with the average seasonal factors and that expected quarterly average demand of 650, and we'll get the seasonalized forecasts for year 5. So essentially what we've done is we've computed seasonal factors for each year we have data, averaged like seasons, then taken our unseasonal forecast of 650 a quarter and seasonalized it. We could have done the same thing in an additive way, where instead of computing a ratio each quarter, we would be computing a difference each quarter. And so then we would add back the difference that the season makes. We're not going to do that here in the slideshow, and I don't think you have a homework assignment that requires you to do that. But it's the same process, essentially, only we're using differences instead of ratios. Well, let's just quickly wrap up this slideshow. There are other topics in the chapter, but this is where our focus is going to be in the lecture. I just want to comment that forecasts are created by individuals, and individuals have agendas. So, for example, if you're in a company, a lot of times marketing people are close to the customer and they create a demand forecast. But marketing people, they want to have something to sell, so they're probably going to inflate the forecast a little bit. If there's nothing to sell, it's hard to get a commission. Or if there's nothing for a customer to see and feel and touch and so on, it's difficult for them to make the decision that they're going to buy it. So a lot of times what will happen in a company is marketing will inflate a forecast, or maybe customers will create a forecast and give it to a supplier, and the same thing's going to happen. They don't want to run out of supply. So a lot of times also what happens is operations people might make a forecast, or suppliers might make a forecast, and they're going to say, well, the customer, they always jack up demand in their forecast, so I'm going to adjust it down in my forecast. They have an agenda also. So what's happening these days a lot more is something called collaborative planning, forecasting, and replenishment. In this scenario, what happens is suppliers and customers, also marketing and operations, these parts of organizations and parts of supply chains that might have different agendas agree to get together, share the data, work from the same data, and come up with a common forecast, and to use that forecast across the board in their planning for operations. So this is something that's kind of new in terms of how we do forecasts. Organizationally, we're moving toward more collaboration and more visibility and cooperation across organizations and across supply chains. So the techniques, they don't necessarily change, but we come to a better agreement in terms of the characteristics of what we want to be the actual forecast and the approach that we want to take to generating that. So hopefully that's helpful. I hope these examples in this lecture, and I know it's quick and we've gone through each example very quickly, but I hope they're helpful to you for understanding what we're trying to do when we're using the various approaches to find estimates for trend, or estimates for the base level, or estimates for seasonality, and putting together a forecast using those things. We'll see you on the next lecture.